Pad 2. After Flight 12, nearly pristine. Nothing collapsed. Nothing needed emergency replacement. The most powerful rocket ever built just launched from here. And the launch mount is still standing. Sounds perfect, right? But in the aerial imagery captured right after the flight, there's a brown arc on the surface of the orbital mount. Small, easy to miss. Here's what makes it interesting. That arc didn't appear randomly. It appeared in exactly the right location, exactly the right shape, for a very specific engineering reason. If you know how to read it, it's a precise map of where the water deluge system is underperforming. Quietly, after every flight. And this isn't the first time this pattern has shown up. Today, we're going to read that arc together and understand why it matters for Flight 13. Let's get into it. A few days after Flight 12, the team at RGB Aerial Photography flew over Starbase. Pad 2 looked almost normal. The tower was standing. The Mechazilla arms were in place. No signs of catastrophic damage. But zoom into the surface of the orbital mount, the massive steel plate directly beneath where the booster sits. And something's off. A brown arc. Not uniform brown, not random smearing. A structured arc, nearly a perfect curve. Positioned at exactly the corner of the orbital mount, the precise zone where the booster executes its pitch-over maneuver after liftoff. That arc isn't a stain, it's data. The water deluge system on Pad 2 operates on a straightforward principle. Just before and during engine ignition, hundreds of thousands of liters of water are pumped beneath the launch mount at enormous flow rates. The goal isn't to extinguish fire. The goal is to absorb thermal energy, converting it to steam before it can burn or warp anything. Water is injected through a pattern of drilled holes. Each hole produces a water cone, a protected zone radiating outward from that injection point. Think of it like a lawn sprinkler system, multiple small heads, evenly spaced. Each head covers a circular zone around itself. Space them close enough and those zones overlap. Full coverage, no dry spots. But space them too far apart and you get gaps, patches of grass that never get watered, even though the total water volume is technically sufficient. Water deluge works on exactly the same principle, except instead of grass, you're cooling steel in an environment measured in thousands of degrees Celsius. The brown zone on the orbital mount is those gaps, made visible. Look closely at the same frame, and you can identify two distinct hole density regions on the orbital mount surface, separated by a radial boundary. Higher density zone, clean surface, no heat discoloration. Lower density zone, exactly where the brown arc appears. This isn't speculation. This is spatial correlation. Two things occupying the same location in the same image. The data is clear. Fewer holes equals fewer water cones equals longer steel exposure to heat. The steel reached temperatures high enough to discolor, but not high enough to cause structural deformation. That's why the pad is still standing. That's why no one is reporting critical damage. But that's also exactly why we need to ask, why is the whole pattern non-uniform at that specific location? Why it happens when simulation meets reality. Before a single drop of water was pumped into Pad 2, SpaceX ran CFD, Computational Fluid Dynamics. This is simulation software that calculates how heat, gas, and pressure move through three-dimensional space. You input rocket geometry, engine thrust, launch angle, expected trajectory. The software outputs how thermal energy distributes across the surface below, where the hottest zones are, where the most water coverage is needed. From that output, SpaceX engineers design the hole pattern. How many holes, where they go, what density. CFD has one fundamental limitation that no one in the industry can fully overcome with software alone. It performs best when the environment is predictable. When the booster lifts off and begins its pitch-over, the maneuver that transitions from vertical to downrange flight, the plume from 33 Raptor engines doesn't hold still. It moves. The plume angle shifts continuously with the booster's trajectory. Pressure fluctuates. Wind conditions shift. and each Starship mission can carry a slightly different trajectory profile. This creates what engineers call an aerodynamic shadow. Imagine shining a flashlight at a wall covered with small obstacles. As you move the flashlight, the shadows shift. The shielded zones change every second. Aerodynamic shadow works on the same principle, except instead of light, it's heat. And instead of shadow, it's the zone where water coverage fails to reach. The hole pattern, drilled permanently into steel, cannot follow. Result: certain zones on the orbital mount never receive water cone coverage, depending on the specific trajectory of each flight. This isn't a SpaceX-specific problem. NASA's Space Launch System at LC-39B uses a fixed deluge system with a static hole pattern. Blue Origin at LC-36 does the same. But there's a critical difference. SLS operates on a tightly defined trajectory, nearly identical across missions. A fixed pattern works well because the aerodynamic shadow barely shifts. Starship is different. It's designed for multiple mission profiles: Starlink deployment, lunar missions, Mars. Each profile has a different trajectory. The shadow moves differently. A fixed hole pattern optimized for one trajectory cannot be optimized for all of them. That's the trade-off built into a rocket designed to do everything. The short-term fix is straightforward. Drill additional holes into the lower density zones. Increase hole density until the water cones overlap enough to eliminate the gaps. SpaceX has done this before. The long-term solution is genuinely dynamic water coverage, a system capable of adjusting flow rates by zone in real time based on the specific trajectory data for each individual flight. Not a static sprinkler grid, an intelligent one that knows where to deliver more water based on the conditions of that specific flight. Nobody in the industry is there yet. That's why this story matters beyond a brown arc on a steel plate. It's a signal pointing at an engineering limitation the entire space industry has yet to solve. If this level of analysis, the details that most channels skip past, is useful to you, a like and a subscribe genuinely helps this content reach more people. The repeating pattern. When the same failure appears in two different places. When the same thing fails in two different locations, is that a local defect or a system-level limitation? The brown arc on the orbital mount after Flight 12 is not the first time SpaceX has seen the signature. Before this, the apex panels on Pad 2, the steel plates at the top of the launch mount, showed the same issue. Same mechanism, same symptom, same thermal discoloration pattern. SpaceX identified it, analyzed it, drilled additional holes into the low-density zones, and continued flying. But here's what demands closer examination. When a problem appears at a single location, you can conclude it's a localized design defect. Fix that point. Done. When the same problem appears at two separate locations, apex panels, then the orbital mount corner, the logic has to shift. This is no longer a point defect. This is a system-level limitation. Point defect. Fix one location. Done. The problem doesn't return. System-level limitation. Fix one location. The problem surfaces somewhere else. Then somewhere else again, until you change how the system works, not just patch individual points. If you're treating a system-level limitation like a point defect, you'll be chasing it indefinitely. Drill here, it appears there. Drill there, it moves again. That's not what SpaceX wants when rapid reusability is the target. This doesn't mean SpaceX is failing. The way SpaceX responds to these signals, identify, analyze, fix, keep flying, collect more data, that's exactly how a test-driven program should operate. No lab environment, no CFD simulation can give you data as accurate as actually firing 33 Raptor engines and measuring what happens. But there's a distinction between learning correctly and understanding the problem deeply enough to fix it permanently. The repeating pattern across two locations suggests SpaceX may still be in Phase 1, learning correctly. The question is whether they've reached Phase 2, understanding deeply enough to change the system, not just the individual points. In aerospace history, the pattern of fix point, problem appears elsewhere, fix point, repeat, is not a sign of failure. It's a sign of a system being understood incrementally, one flight at a time. Boeing took years to fully characterize thermal distribution in engine compartments on the 737. The F-22 Raptor required multiple generations to optimize its radar-absorbing coating. Starship is only at Flight 12. Every thermal arc documented and analyzed is one step closer to fully understanding a system no one has ever built before. Flight 13. Case study. When engineering timelines meet real-world pressure, drilling additional holes into the orbital mount is not a complex operation. Technically, it's straightforward. Identify the zones needing additional coverage, drill, inspect, close out. But there's one factor that determines when it can be done and when it can't. That's the state of the launch campaign. Right now, while Pad 2 is being inspected after Flight 12, this is the ideal window for any modification. No vehicle on the pad, no countdown running, no wet dress rehearsal scheduled. The pad is fully open. The moment the Flight 13 launch campaign begins, when Booster 20 and Ship 40 are stacked, when the wet dress rehearsal is scheduled, when FAA clearance is issued, the priority structure changes completely. Any modification at that stage triggers its own reinspection cycle. And reinspection during an active launch campaign doesn't take days. It can take weeks. There's a clear precedent for this decision pattern. Before Flight 4, SpaceX observed the damage signature from Flight 3 and implemented a series of changes to the water deluge system on Pad 1. Not because the FAA required it. Not because the pad was at imminent risk. Because the engineering team looked at the data and concluded, if we don't address this now, it will keep appearing, at a worse time. That decision added time between Flight 3 and Flight 4. But from Flight 4 onward, Pad 1 showed measurably lower damage levels after each flight. That same decision-making pattern is likely being applied to Pad 2 right now. The real question isn't whether SpaceX will fix it. They will. That's near certain. The real question is, will they fix it before or after Booster 20's engines are torqued in? Once engines are installed on a booster, the process of removing them to access the pad is expensive and time-consuming. Not impossible, but exactly the kind of thing you avoid if you can. If SpaceX completes the orbital mount modification before the launch campaign begins, Flight 13 rolls to the pad with an improved system. Clean slate. If the launch campaign begins before the modification is complete, SpaceX faces a choice. Fly with an unoptimized pad or delay to fix it mid-campaign. Both are valid options. But their timeline implications are very different. Based on recent imagery from Starbase, the engineering team is actively working across multiple Pad 2 systems simultaneously. New landing rails have been installed. The catch system dampers are being tuned. Booster clamps have been removed for inspection. These are all signatures of a pad undergoing comprehensive review, not routine maintenance. If the orbital mount hole pattern modification is on that list, and the engineering logic says it should be, the current window is the optimal time to execute it. The FAA mishap investigation from Flight 12 is ongoing. It's focused primarily on the boost-back burn failure of Booster 19, not pad damage. But as part of that investigation, SpaceX must submit a corrective actions report, a document detailing every change being made before Flight 13. If the orbital mount hole pattern modification appears in that corrective actions report, that's official confirmation SpaceX has formally identified and is addressing it. If it doesn't appear, either because the FAA doesn't require it, or because SpaceX has assessed the priority differently. In either case, the aerial imagery after Flight 13 will be the real test. If the brown zone is gone, the modification was made and it worked. If it's still there, the story continues. The story of the brown arc on the orbital mount is not a story about imminent catastrophe. Pad 2 is standing. SpaceX is moving in the right direction. Flight 13 is in preparation, but it is a story about the cost of moving fast in territory no one has mapped before. Every small signal like this thermal arc, read correctly, is data more valuable than any simulation. SpaceX knows that. That's why they fly. That's why they look. That's why they drill more holes. Not because they have to, but because they understand that every flight is an experiment, and every signal is the answer to a question you can't ask any other way. But Pad 1 is being built right next door, and the question no one has asked yet is this: Is SpaceX applying everything learned from this thermal arc directly into Pad 1's design from day one? If so, Pad 1's hole pattern will look different from Pad 2's before its very first flight, and aerial imagery will tell us, before Pad 1 ever launches. The brown arc is small, but it tells a big story. Pad 2 isn't broken, but it's recording its own limitations after every flight. Reading that signal at the right time, that's what makes the difference. Thanks for analyzing this with me today. If this perspective was useful to you, like, share, and subscribe to the Space Brief. Drop a comment below with what stood out most to you.